Man has described himself in many ways. But if we concentrate on man in relation to his control over his environment, no description is more apt than the description of man as a tool-making animal. And in the short history of mankind, the majority of the tools which man has made can be thought of as an extension of his muscle power. That is, the ability to perform work faster and in greater quantity. However, in the mid-1940s of the 20th century, a different kind of tool was invented. A tool for extending certain of the powers of man's mind. This tool is the electronic computer. It is the fast, reliable, and tireless performance of a variety of arithmetic and logical operations that gives the computer its great utility and power. But merely looking at a computer won't tell us very much about what it actually is doing. Neither will this tell us anything about the revolutionary material and intellectual effects of such machines. We can easily see the material and intellectual effects of, say, machines for transportation. We know that the modern jet aircraft represents a great increase in speed over the earliest aircraft. We also know that modern airplanes have made the world smaller and changed our way of thinking about ourselves and our world. And future means of transportation will bring even more rapid and radical changes. But even the difference between the speed of an ox cart and the fastest rocket is small when compared with the difference in speed between calculation by hand and calculation by computer. For example, the first electronic calculator to be completed could do the work of 50,000 people working by hand. Scientists, when they speak of a great change in speed or size, prefer to speak in terms of a unit of measurement called an order of magnitude, meaning 10 times as much. Dr. Richard Hamming, a research mathematician for the Bell Telephone Laboratories, in a paper presented before a meeting of the American Academy for the Advancement of Science, put it this way.
The computer revolution is often compared with the famous Industrial Revolution in importance and scope. The Industrial Revolution effectively freed man from being a beast of burden. The computer revolution will similarly free him from dull, repetitive routine. The computer revolution is, however, perhaps better compared with the Copernican or the Darwinian revolution, both of which greatly changed man's idea of himself and the world in which he lives. Before getting into the main part of this paper, it is necessary to discuss briefly the idea of a change in a technology. Change is often measured in units of an order of magnitude, meaning roughly a factor of 10 times as much. It is a common observation that a change of an order of magnitude in a technology produces fundamentally new effects. As an illustration, consider the following example. Modern jet planes are about 1 order of magnitude faster than Wright Brothers' first plane. Another example, the fastest missiles are somewhat more than 2 orders of magnitude faster, meaning about 300 times faster. Automobiles are used at speeds around 1 order of magnitude faster than a horse and wagon. Each of these have produced whole new effects. Indeed, it is said that the automobile has produced even a change in our morals. Computers have improved in speed by at least 6 orders of magnitude, a millionfold. In order to understand the factor of a million, consider the following two situations. First, that you have only $1, and second, that you have $1 million. You can readily see that in the two situations there are fundamentally different effects. You adopt a different view of yourself and the world in which you live. Along with the change in speed, there has been a great increase in reliability, so we now do much longer computations than was practicable by hand. Finally, with the increase in speed, there has been a corresponding decrease in the cost, something more than 1,000 times cheaper. It is as if suddenly automobiles cost $2 to $4, houses $20 to $60. And the changes in the computer technology are still going on. These, then, are the...
We hardly need to be reminded that we live in a world that is becoming more complicated and more crammed with information every day. One description for this vast quantity of data on everything from the lifetime earning records of an individual to the beeps and pulses relayed to Earth from a space satellite uses that overworked word, explosion. This time, an information explosion. The computer is an invaluable tool for processing these millions of bits of information in accurate, fast, and economical fashion, in accordance with rules and instructions provided by the human programmer. In the most gigantic of all record-keeping jobs, the Social Security system, more than 1 million personal records can be processed in one day. This manufacturing plant is entirely computer-controlled in accordance with rules for decision-making stored in the machine's memory. This chemical plant for making polyisoprene was designed by a computer. In a recent example, a computer in 16 hours and out of 16,000 possible designs selected the design that most closely approached the ideal design as defined by the engineers. And this actual firing of the multi-million-dollar Saturn rocket was simulated on this computer many times before the actual firing was authorized. And these simulated firings, which helped eliminate many of the problems in the functioning of the rocket, cost only a fraction of what an actual launching would have cost. Each of these operations, record keeping and accounting, control, design, and simulation, is achieved through the manipulation of numbers according to instructions and rules given to the computer by the programmer. But what are these rules, and what is the relationship between numbers and the real things they are said to represent? These are some of the questions that we put to the scientist whom we've already seen, Dr. Richard Hamming, research mathematician at the Bell Telephone Laboratories.
Well, I would say that at present at the Bell Telephone Laboratories, we do about 10% of the experiments on a computer and about 90% in the laboratory. I would expect that in time we will do 90% on the computer and 10% in the lab. Speed, cost, and effort favor the computer over the laboratory approach. This advantage is possible because we construct a mathematical model rather than a material model. I use the word construct because the mathematical equations are the construction rather than a materialistic physical model. It is perhaps fortunate we have found, particularly in the field of physical sciences, that our predictions based upon the mathematical models agree very well with what we observe in the physical world.
The 19th century physicist Heinrich Hertz described the concept of a model in these words: "We make for ourselves internal pictures or symbols of external objects, and we make them of such a kind that the necessary consequences in thought of the internal pictures are always pictures of the necessary consequences in nature of the object symbolized."
The idea of a mathematical model is fairly easy to understand. A very simple, trivial example is the numbers you calculate on your check stubs. You combine the various numbers by addition and subtraction, and they correspond in a very real sense to the amount of money that you have in the bank. The mathematical model is the numbers you manipulate. The amount of money you actually have in the bank is the physical world. Let us consider now a slightly more complex example.
This is a common experience for most of us. The front end of the car dips sharply when we come to a sudden stop. In technical language, there is a transfer of weight from rear to front in the action of braking. A mathematical model of this transfer of weight can reveal exactly how much weight is on both wheels. And different road surfaces and braking conditions will result in different weight distributions. But the mathematical model for the transfer of weight from rear to front will remain the same.
In this mathematical model of a behavior automobile, we can use a computer to simulate what would happen in actual practice. We have actually found that our mathematical models of automobile traffic predict very well many of the effects which we observe. Returning to our more general remarks about the use of computers, we first use computers to simulate situations in engineering, situations which we had been doing before by hand. The computers allowed us to do much larger and more complex problems. But this ignored the order of magnitude effect which we spoke of. We are now beginning to use the machines in entirely new ways on entirely different problems. And this is the exciting part. This is the intellectual aspect of applying the machines to completely new ideas that has so excited many people in the field.
One of the characteristics of human beings is that among other things that they do is that they solve problems. And what it means, of course, to solve a problem is being able to not only get an answer to a question that arises in a particular situation, but then to find other cases that are similar to the initial one, so that we are in effect in a position to solve not just one concrete problem, but a whole class of them.
This is Professor Ernest Nagel, a leading logician and philosopher from Columbia University.
Once a domain has been developed to the point where answers can be given from given set of assumptions simply by following some set of instructions or some rules, then it's not entirely evident that one should be thinking of the significance of every step that one is performing.
Well, is it also possible to instruct machines to follow the rules of thought?
Indeed, I think this is, of course, the basis for having machines or computers, since their entire task is